Okay, so on Tuesday, we look at how you can calculate the left atrial pressure. In order for you to calculate or to get the left atrial pressure, you have to have mitral regurgitation. Mitral regurgitation. Because when you have mitral regurgitation, blood is flowing from the left ventricle across the mitral valve into the left atrium. The only way you can get that happening is if the left ventricular systolic pressure is greater than the left atrial pressure. And that difference in pressure is what we call the gradient. Okay, so if you go back, so the gradient is the difference between the left ventricular systolic pressure and the left atrial pressure. The difference is the gradient. Once you have mitral regurgitation, you take the MR velocity, you square the velocity, and you multiply it by 4. Okay, so 4v squared, that is the gradient. Once you rearrange the equation, then you see that left atrial pressure is equal to the left ventricular systolic pressure minus the gradient. And again, the gradient is just squaring the MR velocity multiplied by 4. And then this is the left atrial pressure. Again, the left ventricular systolic pressure is the same thing as the systolic blood pressure, as long as there is no obstruction at the left ventricular flow tract. There is no aortic stenosis, anything like that. So when we talk about left ventricular systolic pressure, that is the pressure developed in the left ventricle when the left ventricle contracts. And that is usually the same as the systolic blood pressure. So that's how you get your systolic blood pressure. Unless you have, if there's an obstruction of the left ventricular flow tract, then all bets are off. So we can use the concept of regurgitation to calculate, pressures, because gradient is a pressure difference, and we went over that. Now we're going to move on, and we're going to look at aortic regurgitation. We're going to look at aortic regurgitation or aortic insufficiency. So we're going to try and understand what's going on when you have aortic regurgitation. So remember, the normal flow of blood is from the left ventricular cavity to the left ventricular flow tract, across the aortic valve, into the aortic root, into the ascending aorta. That's a normal flow of blood. So when the left ventricle contracts, blood is going to flow from the LV across the left ventricular flow tract, across the aortic valve into the aorta. That is normal flow. When you have aortic insufficiency, then in diastole, blood flows backwards from the ascending aorta across the aortic valve and back into the LV. That is aortic regurgitation or aortic insufficiency. Okay? The blood is flowing the opposite direction. For you to get blood flowing backwards, then the pressure in the aorta have to be greater than the pressure in the LV, right? So just think about it. Aortic insufficiency, blood is flowing from the aorta across the aortic valve into the LV. So therefore, the pressure in the aorta have to be greater than the pressure in the LV for blood to flow backwards. So the gradient then, the gradient that is generated is equal to the aortic diastolic pressure minus the left ventricular end diastolic pressure. And remember that aortic regurgitation occurs in diastole. So we're talking about the pressure in the aorta in diastole and the pressure in the LV in diastole. So aortic regurgitation or aortic insufficiency is a diastolic phenomenon. It occurs in diastole. Okay, so blood is going to flow from the aorta across the aortic valve into the left ventricle in diastole. So the gradient is equal to the aortic pressure, which is aortic diastolic pressure, minus the left ventricle end diastolic pressure. That's the pressure in the LV in diastole. That is the gradient. Okay, so when we do our Doppler and we get our aortic insufficiency, we get, just like your pulmonic insufficiency, you get an early velocity and a late velocity or an end diastolic or end diastolic velocity. So if you rearrange your equation, okay, if you rearrange your equation and you want to get the left ventricle end diastolic pressure, because you know the aortic diastolic pressure is the same thing as the diastolic blood pressure. The aortic diastolic pressure is the same thing as the diastolic blood pressure. So you can measure this. The only thing you can't measure is this left ventricular end diastolic pressure. That is the pressure in the LV at the end of diastole. So when the LV is filled with blood, it has a certain pressure. And measuring that pressure is very important, you know. So we can use the gradient across the aortic valve when you have aortic insufficiency to calculate that. Again, the gradient is just your diastolic aortic diastolic pressure minus the LV end diastolic pressure. Okay, if you rearrange the equation, because this is what you need to solve for, this is what you need to know. So the left ventricular end diastolic pressure is equal to the aortic diastolic pressure minus the gradient. Again, your aortic diastolic pressure is the same thing as your diastolic blood pressure. So once you know the gradient, of course, you're going to do the blood pressure. So you have your diastolic blood pressure. Then you subtract from the aortic diastolic pressure, which is your diastolic blood pressure, your gradient, 4v squared. And this is the velocity that we're talking about. So when you do Doppler across the aortic valve, okay, this is what aortic insufficiency looks like, if you remember. Okay, so on top you have your two-dimensional image on top. Okay, this is actually an apical three-chamber view. The cursor is across the left ventricular flow tract. This is aortic insufficiency. And you're going to get early velocity and you're going to get your end diastolic velocity. Remember that we are interested in the end diastolic velocity. So this is the velocity that you're going to plug in your equation. So again, your left ventricular end diastolic pressure, once you rearrange the equation, is equal to the aortic diastolic pressure. The aortic diastolic pressure is the same thing as the diastolic blood pressure. And then you square your velocity, multiply by 4. That's the gradient, and you subtract it from that. And that's the left ventricular end diastolic pressure. Okay? So, okay, you use all of that. Again, when patients get into trouble cardiac wise and they develop heart failure, you need to know the left ventricular end diastolic pressure and the left atrial pressure, because those pressures are usually elevated when patients develop heart failure. Those pressures are elevated. So if you can measure those pressures in the echo lab, you're ahead of the game. Okay, these are just some abbreviations that you need to know. These are things that we went over before. We'll in discussion we'll mention them again. All right, so stroke volume. The definition for stroke volume is the volume of blood that the LV or the RV pumps out per beat, per beat. okay? The stroke volume. So in diastole, let's look at the left side. In diastole, the left ventricle fills with blood, okay? In systole, it pumps the blood out. If you want to calculate the amount of blood that was pumped out, all you have to do is get the volume of blood in diastole, and you're going to subtract from that the volume of blood in systole, and the difference is your stroke volume, okay? But you can use your remember, you can get LV volume by doing your method of disc, your modified Simpson rule. You can do that. So you can plain, when you do your echo, you can get your LV in diastole, and you can get your LV in systole, and you can get a stroke volume. And the echo software will give you not only a stroke volume, it will give you an ejection fraction, okay? But the stroke volume is the volume of blood pumped from each of the ventricle per beat, per beat. Cardiac output, however, is the volume of blood that the heart pumps out per minute. So you have to know the difference in the definition. Cardiac output is the volume of blood that the heart pumps out per minute. So all you have to do to get, when you calculate your stroke volume, if you multiply your stroke volume by heart rate, you get cardiac output. Again, multiply your stroke volume by heart rate and you get your cardiac output. We usually talk about cardiac index. When we index anything, we divide it by the body surface area. Okay. Now, this is a very important formula that you guys need to know. This is the basis for continuity equation. So you need to know it, the hydraulic orifice formula. Okay. And it also will allow us to use Doppler technique to calculate stroke volume. So if all you have is Doppler and limited 2D measurements, you can calculate stroke volume. So you don't have to get your LV and look at it in diastole and systole. So the hydraulic orifice formula states that flow rate is equal to the cross-sectional area times the flow velocity. Flow rate is equal to the cross-sectional area times the flow velocity. So if you want to calculate the flow rate in, say, a pipe, okay? So when we talk about a pipe, we talk about a tubular structure, and it's going to have a cross-sectional area, okay? So where the fluid enters, you get a cross-sectional area, and you can calculate the cross-sectional area. And if you know the flow velocity, you multiply the cross-sectional area times the flow velocity, you get the flow rate. It is important that to recognize that if you have a closed circuit, the flow rate at any point in that circuit is going to be the same. Flow rate is going to be the same. All right. So we're going to expound on this a little bit more so you can get a much clearer understanding. But you have to understand that flow rate is equal to the cross-sectional area times the flow velocity. CSA is cross-sectional area. All right. So when we're doing Doppler, we can get flow, okay? And flow is equal to the cross-sectional area times the TVI, which is a time velocity integral, okay? Time velocity integral, which is sort of similar to the velocity. what we're doing, we're integrating the velocity with time. That's why we call it time velocity integral. Okay, it's a so-called what we call the area under the curve. All right, so flow, if we're going to use our Doppler principle, then flow is equal to the cross-sectional area times the TVI, time velocity integral. Okay, so all right, so we want to calculate we want to calculate the cross-sectional, the stroke volume using Doppler technique. We know how to do it using the modified Simpson or the method of disk. All we do, we get the LV size in diastole, we get the volume, get the LV size in systole, we get the volume, and we subtract the systolic volume from the diastolic volume, and that's the stroke volume. But we can use Doppler technique to calculate stroke volume by just looking at our hydraulic orifice formula, which states that flow is cross-sectional area times the TVI. So what we're doing, we're looking at the LV and the flow across the left ventricular flow tract. We're looking at the flow across the left ventricular flow tract. So what we do, we when we look at the left ventricular flow tract, we assume that it's circular. We're going to assume that the left ventricular flow tract is circular. Okay, so the left ventricular flow tract is, if we're looking at our 5-chamber view, left ventricular flow tract is about right there, and we assume it's circular. Okay, so when this LV contracts, the flow across the left ventricular flow tract is equal to the cross-sectional area across the left ventricular flow tract times the TVI, time velocity integral. If you remember, when we do our Doppler, and this is the cursor, and our sample volume is right here, and we press P Doppler, we get an envelope looking like this. Okay. On the horizontal axis, you have time. On the vertical axis, you have velocity. Okay. And when you look at the area under the curve, so this is our LVOT envelope, left ventricular flow tract envelope. Okay. And when we trace it or when we plane it, we get the TVI. This TVI is just the area under the curve. We integrate the time and the velocity. Okay, so the LVOT, VTI and TVI use interchangeable. You see, this is 22 centimeters, 22.1 centimeters. That's the TVI. Okay, you can, if you look at it closely, you know, when you look at it closely, of course, this is velocities on the vertical axis, time is on the horizontal axis. Okay, so what we're doing, we're actually getting the area under this curve, the area under this curve right here. So in essence, what we're doing is multiplying the velocity and the time. And when you do that, you end up with just a distance. That is why VTI or TVI is usually just a distance, okay? Because you're integrating your velocity and your time. So, you know, when you multiply, remember velocity is meters per second, time is in second. When you multiply them, then the time cancels and all you're left with is a distance. So your velocity time integral is really a distance. It is the distance traveled the fluid travel. It is the distance that the fluid travel. That is essentially what your VTI means. Okay, so you're integrating your velocity and your time, the area under the curve. Okay, all right, so stroke volume is equal to the cross-sectional area times the TVI. I just showed you how to get your TVI or VTI. Okay, apical 5-chamber view, cursor is right there, sample volume. It should be a little distance from your aortic valve. Okay, and you're supposed to, and it's a pulse wave Doppler measurement, and you're gonna do planimetry to get your VTI. So all you need now to get the stroke volume is a cross-sectional area. But remember what I said, the cross-sectional area of the left ventricular flow tract, we can assume that it's circular. Okay, and that's where that's where your parasternal long axis view comes into play. Okay, so this is your parasternal long axis view. This is our left ventricular flow tract diameter. Okay, so that is why we measure the LVOT diameter. Your aortic valve is right there, so it's a little distance away from the aortic valve. And this area is what we call your left ventricular flow tract. This is the area, and we measure the diameter. We assume that it's circular, so this is circular, and this is the diameter. Remember that the area for a circle is pi r squared. The area for a circle is pi r squared. So if we assume that this left ventricular flow tract is circular and we have the diameter, then we can calculate the area. The area for circle is pi r squared. So let's simplify it a little bit. Pi is 3.14. R, which is the radius, is diameter divided by 2, and we square it. So pi 3.14 times, when you simplify this, you get diameter squared over 4. 3.14 divided by 4 is 0.785, and then you multiply by the diameter squared. So the area of the LVOT is 0.785 times d squared. The area of the LVOT, assuming that it's circular, pi r squared. When we plug everything in the equation and we simplify it, it comes out to 0.785 times d squared. So if you remember now, your stroke volume is the cross-sectional area times the TVI across the LVOT. So when you plug everything in, you get this times the TVI, okay? So stroke volume is cross-sectional area times the TVI. Cross-sectional area is pi r squared. When we simplify that, we got 0.785 times d squared. And then you just multiply it by the TVI across the left ventricular flow tract. And this is stroke volume. So this is the formula for stroke volume. You have to remember it. So all you need to do is to measure your diameter, LVOT diameter, and your TVI. So your apical 5-chamber view, you get the LVOT TVI, okay? This is your LVOT envelope. And once you do planimetry around it, the computer will give the VTI. With your parasternal long axis view, you measure the diameter and then use your formula. Okay, when you simplify it, you get 0.758. So you just plug that in that equation to get the area. And then your stroke volume is 0.785 times d squared times VTI. So you can use Doppler technique along with limited two-dimensional image, and you can get your stroke volume. Stroke volume is the volume of blood that the heart pumps out per beat. To get the cardiac output, which is the volume of blood that the heart pumps out per minute, all you do, you multiply your stroke volume times the heart rate. So if the patients have a heart rate of 60 beats per minute or 80 beats per minute, you multiply your stroke volume times the heart rate and you get the cardiac output. So when the patient comes to the echo lab, you not only have to get the blood pressure, you have to get the heart rate, but more importantly, you have to get the heart rate while you're doing this analysis. So, and usually if you look on the monitor, it will record a heart rate. Okay, so you can use that heart rate. So this is our cardiac output, the volume of blood pumped from each ventricle per minute. But we like to index everything. And when we say we index something, we divide it by the body surface area. So we usually talk about cardiac index. It's a more representative measure. So the cardiac index is equal to the cardiac output divided by the body surface area. And everybody have a body surface area, okay? They take your weight and your height, and there are nomograms that will use those two measures and give you the body surface area. All right, so it's important to know how to calculate stroke volume, cardiac output, and cardiac index. Now we're going to look at something we call shunt flow. We're going to look at shunt flow. And what do we mean by shunt flow? Say, for instance, you have an atrial septal defect or a ventricular septal defect. So you have an abnormal communication between the left and the right side. Okay, maybe so again could be ASD, VSD, or PDA, or any shunt. So clinically, it's important to know how much blood is being shunted from, say, the left side to the right side. So if you think about it a little bit, say for instance, you have an ASD, then blood is gonna shunt from the left atrium across the ASD into the right atrium. And because of that, you're gonna get increased blood flow in the pulmonary circuit. If you have a lot of shunting of blood, then you're gonna get a much greater increase in pulmonary blood flow as compared to systemic flow. Okay, so we can use that concept to determine how significant the shunt is. Because for a small shunt, you're going to get a small amount of blood going from, say, the left to the right, and the pulmonary blood flow is not going to be tremendous. But for a large shunt, you're going to get a large amount of blood flowing from the left side to the right side. You're going to get a great increase in the pulmonary blood flow as compared to the systemic flow. And when we talk about systemic flow, we're really talking about the blood flowing across the left ventricular flow tract. Blood flow across the left ventricular flow tract. So when we do shunt flow, all we do, we get the stroke volume across the right ventricular flow tract, and we're going to divide it by the stroke volume across the left ventricular flow tract. That ratio is the shunt flow, okay? The pulmonary to systemic flow ratio. And it's sometimes written as QPQS, pulmonary to systemic flow ratio. So in essence, what you're doing, you're getting the blood flow across the right ventricular flow tract, across the pulmonary valve, and you're dividing that by the blood flow across the left ventricular flow tract, okay? The pulmonary systemic flow ratio. Again, it's an indication of the magnitude of the shunt. And this is how you do it. So to get the stroke volume across, to get what you're actually doing is getting the RV stroke volume. Okay, the volume of blood that's pumped out from the right ventricle per beat. Okay, again, the flow. Remember the hydraulic formula. Okay, so that flow is equal to the cross-sectional area times the TVI. Flow is equal to the cross-sectional area times the TVI. So we're looking at the flow across the right ventricular flow tract. We assume that the right ventricular flow tract, just like the left ventricular flow tract, is circular. So if we measure the diameter, we can get the cross-sectional area. Because if it's circular, the cross-sectional area is pi r squared. Again, when you simplify pi r squared, r is d over 2, and you square it, the simplification gives you this. So the cross-sectional area for RVOT is that. So once you measure this diameter, the diameter of the right ventricular flow tract, and it is usually measured just a little bit above your pulmonary valve, and you need to see the two walls of the pulmonary trunk then, okay? And you measure your diameter, you plug it in the equation, you get the cross-sectional area. But to get the flow, you have to multiply that by the TVI. But all you do, it's simple. So your cursor is there. Well, your two-dimensional image is on top. Short axis at the level of the aorta. Pulmonary valve is right there. Right ventricular flow tract is there. So your cursor, sample volume, you press your PW button, and you get the flow across the right ventricular flow tract. This is the flow across the right ventricular tract. So once you plane it, once you do planimetry of it, you'll get the TVI, time velocity integral. Again, time is on the horizontal axis. On the vertical axis, you have the velocity. You're basically multiplying them. You know, again, this is not rocket science. It's very simple. So if we said area under the curve, if the flow was like this, suppose you get a flow that looks like this. So if you get a flow, say the flow looks like this. So, okay, so you have a flow. It's not really look like it. So it comes down, it stop abruptly, and it go horizontally. There's essentially the velocity is the same. There's no acceleration, and then it goes back up. You know, this flow you'd understand because this is a rectangle. This is a rectangle. And the area of a rectangle, you're gonna use one side. We have time on the horizontal axis, and the vertical axis, this is velocity. So the area would be, say, call this the breadth times the length. So that's the area. So the area under the curve is the time multiplied by the velocity. Velocity is meters per second, time is in seconds, so that's why when you multiply them, you just get a distance, meters, okay, which is the area under the curve because you multiply this side by this side. You integrate it. So when you integrate it, that's what you do. That's what you do. But this is not a simple rectangle. So that's why the integration of it is a little bit more um, complex. Okay, but the principle is the same. Okay, so this is your velocity time integral across the right ventricular flow tract. You multiply it by the cross-sectional area and you get the flow across the pulmonary circuit. Okay, that's going to give you the flow across the pulmonary circuit. Okay, so again, flow is equal to cross-sectional area times TVI. Okay, so again, you get the diameter of the RVOT, plug it in the equation, okay? So, or your pulmonary flow, which we call QP, okay, is basically the stroke volume across the pulmonary valve, and that's equal to cross-sectional area times the TVI across the pulmonary valve. I showed you how to do that, okay? So when you plug that, so all you have to do is get your diameter across the RVOT, and you square it, and you multiply by the TVI, and this is the stroke volume across the pulmonary valve, QP. Okay, QS, we went over QS, which is your systemic flow. This is the blood flowing across the LVOT. Okay, so you have pulmonary flow, which is on the right side. You have systemic flow, which is on the left side. So on the left side, when we say stroke volume, we usually refer to blood flowing across the left ventricular flow tract. And again, the flow is the cross-sectional area. When we simplify that, it's 0.785 times d squared. And if we multiply it by the TVI across the left ventricular flow tract, then we'll get the stroke volume across the LVOT. And all you do, you multiply the pulmonary flow by the systemic flow, and you get the shunt flow. Okay? So your QP-QS ratio is just the pulmonary flow divided by the systemic flow. Okay? This magnitude will tell you how much shunting you have going on. The pulmonary flow and the systemic flow usually they're roughly the same. So the ratio should be 1-to-1. But if you have a lot of blood flow from the left to the right, then you're going to increase your pulmonary flow. And then the ratio is going to increase. It may increase 1.2, 1.5, 2. So if you have a lot of flow from the left to the right across the shunt, then your pulmonary flow is going to be elevated and the ratio is going to be increased. Okay? So that's important. Now, we're going to introduce the concept of the continuity equation, because in order to calculate valve areas in echo, you have to understand the concept of the continuity equation. And I touched on it before, but let's just talk about it again. When we talk about the continuity equation, we're talking about flow in a closed circuit. Flow in a closed circuit. So you have no leak in the circuit. Say you have a long pipe. You have a long pipe. There's no break in the pipe. But some areas of the pipe, you have some narrowing. And you may have different degrees of narrowing throughout the pipe, but no leaks. A very important concept is that the flow at all the different points are going to be the same. The flow at all the different points are going to be the same. So if we take a little segment and we say, well, per second, how much fluid is flowing across this little area? And then we take another area and say how much flow we're getting across that area in the same time. It has to be the same. It has to be the same. So when we have a closed circuit, the flow is going to be the same. The flow is going to be the same. What's going to be different, however, is velocities and cross-sectional area. So cross-sectional area and velocity is going to vary, but the flow is going to be the same. So the continuity equation, which is based on the conservation of mass principle, because the flow is going to be constant, we use it to calculate stenotic and regurgitant valve area. Again, if you take a closed circuit and you say you have point 1 and point 2, and you have in point 1 you have this point 2, there's a narrowing. Okay, what's the flow is going to be the same. The flow at point 1 and point 2 is going to be the same, but whenever you get a narrowing, the velocity or the TVI is going to be increased. Okay, so if there's no narrowing right here, you're going to have a certain amount of TVI or velocity. But once you have narrowing, the velocity or TVI is going to increase. The flow is going to be the same though. Flow is going to be the same. And if you remember the definition for flow, flow is equal to the cross-sectional area times the TVI. Flow is equal to cross-sectional area times TVI. Okay? So let us look at, say for instance, we have aortic stenosis. So if we're talking about aortic stenosis, because of the continuity equation, we know that the flow across the left ventricular flow tract have to be the same thing as the same flow across the aortic valve. Okay? Because the heart is a closed circuit. There is no leak. Okay? So the flow across the left ventricular flow tract is going to be the same flow across the aortic valve. What's going to be different, however, is the velocity. The velocity is going to be different. So if we use that concept, say for instance, this is the flow across the aortic valve, and this is the flow across the LVOT. They're going to be the same because the same amount of blood that flows across the left ventricular flow tract is going to be the same amount of blood that's flowing past the aortic valve. If you don't know the aortic valve area, because remember the flow is equal to cross-sectional area times TVI. And if this is, say this is a flow across the aortic valve and this is flow across the LVOT. If we don't know the aortic valve area, once we rearrange our equation, basic math, just dividing both sides by the TVI across the aortic valve, then we get the flow. Sorry, let's use this as the aortic valve, and this is the LVOT. Okay, so A1 is the cross-sectional area of the LVOT. A2, cross-sectional area across the aortic valve. Okay, so if the aortic valve is stenotic, we usually don't know how stenosed or how narrow the aortic valve is. But if we use our continuity equation and we divide the flow across the LVOT by the TVI across the aortic valve, we can get the aortic valve area, which is very important. It's going to help us to treat the patient clinically. Okay, so using the continuity equation, we can calculate things like aortic valve area and other areas as well. Okay, because we know the flow across the LVOT. You know, we can measure the diameter of the LVOT. We can get the area of the LVOT. In the 5-chamber view, we can get the Doppler of the LVOT. We can also get the Doppler across the aortic valve. What we can do is get the aortic valve area by just looking at it. So we have to calculate it. And we use the continuity equation to calculate the aortic valve area. So we're going to stop here because I want you guys to fully grasp all the concept. Okay? So continuity equation is crucial. You have to understand it because we use it throughout all of echo to calculate stuff. So it's just the flow at one area is equal to the flow at another area, as long as there's no leak in the system. What's gonna vary is the area, cross-sectional area that is, and the TVI. But the flow is gonna be the same. Cross-sectional area and TVI can vary, but the flow is gonna be the same. Flow is equal to cross-sectional area times TVI. All right. So let's stop here.